So, what is the ideal gas law? The ideal gas law accurately describes the properties of an ideal gas, a hypothetical construct. So, ideal gases are not ones made of atoms or molecules that take up any space, and they do not interact with any other matter. So, we're going to assume that the things that make up the gas don't take up they don't have any volume themselves, and they're not going to interact with themselves or anything around them. No gases are ideal, but under certain conditions, we can assume ideal behavior. What are those conditions? The gas must be at a low pressure. They should have a high temperature, and these conditions combined together are going to result in a dilute gas comprised of fast-moving molecules. And if you think about it, that kind of makes sense that we can assume that they're not going to interact with each other when they're moving really fast and they're nowhere near one another. Also, if it's very dilute, there's not a lot of gas in there, then the volume of the actual gas particles is going to be pretty small in relationship to the container, and you could assume that it would approach zero. Sometimes it's important to define standard conditions. So standard temperature and pressure is something you'll see a lot, STP. And this is defined as 0 degrees Celsius and 1 atmosphere. You should note that IUPAC recommended value of standard pressure was changed to 1 bar in 1982, but many texts continue to use the 1 atmosphere value. At STP, the volume of 1 mole of ideal gas is 22.4 liters. So we can picture that here where we have all of these balloons. They're all under standard conditions. They all are exactly 22.4 liters, but each one contains a different mass of atoms because each one of the atoms weighs a different amount. In section 9.3, we're going to use the ideal gas law to compute gas densities and molar masses. We'll perform stoichiometric calculations involving gaseous substances, and we're going to state Dalton's law of partial pressures and use it in calculations involving gaseous mixtures. So we're going to recall that our molecular weight is the mass of something divided by its how many moles there is of it. And rearranging that, for moles, we can see that the moles of something is the mass of it divided by its molecular weight. If we substitute in the mass divided by the molecular weight for N into our ideal gas equation, we get this equation now, where PV equals the mass times R times the temperature divided by the molecular weight. If we choose to look at this as the mass divided by the volume times RT over the molecular weight, we get this M over V term. And if we recall, that is the density, the mass divided by the volume. Substituting in that density, we get this equation. And then rearranging and solving for the density, we can see that the density of a gas is the pressure times its molecular weight divided by RT. So density is an intensive property. We're going to remember that. That means it does not depend on the size of the system. But the density of an ideal gas does depend on the pressure, temperature, and molar mass. We can also solve that equation for the molecular weight. And we can see that the molecular weight is equal to the density times the ideal gas law times the temperature divided by pressure. Or we can substitute in our value for density here. If we have the mass and volume, we can see that that is MRT divided by PV. We can measure the mass of a gas pretty simply doing some experimentation. We can measure a flask that is sealed at the top, inject that gas into it. It is typically then condensed, so we cool it way down until it condenses into a liquid at the bottom, and then we reweigh that flask.